In 1974, Stephen Hawking sat alone with an equation that refused to behave. He had been calculating how quantum fields behave near the curved geometry of a black hole. The combination of quantum mechanics and general relativity produced something unexpected. Black holes were not black. They glowed with faint thermal radiation tied to their mass. The calculation was correct. The radiation was real, and the implications were troubling. If a black hole radiates energy, it loses mass, and if it loses mass, it eventually ends. Not in any explosion, but in a slow thermal whisper stretched across astronomical timescales. A stellar black hole evaporates over 10 to the power of 67 years of cosmic time. That is vastly longer than the current age of the universe, roughly 14 billion years. A supermassive black hole persists far longer still, but the conclusion is the same. Eventually, every black hole radiates away its mass until nothing remains to hold the horizon. At that moment, something has to happen to everything that ever fell inside the hole. That something is what has occupied theoretical physicists for more than 50 years. The rule that makes this a crisis is one of the deepest in all of theoretical physics. Quantum mechanics says that information is never destroyed, only transformed and redistributed. The quantum state of any isolated system evolves forward through a process called unitarity. Given the present state of any system, unitarity allows you to reconstruct what came before. Run the equations forward, you get the future. Run them backward, you recover the history. A cup of coffee cooling in a room seems to lose its thermal order into the surrounding air. But quantum mechanically, every molecule that absorbed heat carries encoded information. The data about the coffee's original temperature is not erased. It is hidden in correlations, smeared across billions of particles in a pattern too complex to practically reconstruct. The information exists, it is preserved, and the laws of quantum mechanics guarantee this. Drop something into a black hole, and those same laws collide with a completely different set. General relativity describes gravity as the curvature of space-time produced by mass and energy. The event horizon of a black hole is a mathematical boundary where escape becomes impossible. Anything that crosses the horizon is causally cut off from the rest of the universe forever. The interior of a black hole is not merely distant, it is outside the causal future of observers. No signal, no particle, no quantum correlation travels from inside the horizon to outside it. Hawking radiation escapes not by leaking through the horizon, but by forming at its edge. The mechanism involves virtual particle pairs appearing spontaneously from the quantum vacuum. Near the horizon, one particle falls inward and the other escapes before they can annihilate. The escaping particle carries energy outward, reducing the black hole mass by a tiny amount. The radiation that emerges is perfectly thermal. It has a temperature and carries nothing more. Thermal radiation does not encode the quantum state of whatever originally fell into the hole. A black hole formed from collapsing hydrogen and one formed from collapsing diamonds would produce radiation that Hawking's original calculation says is completely identical. The information distinguishing hydrogen from diamonds has been erased from the universe. This is the information paradox, and it has resisted resolution for more than 5 decades. Jacob Bekenstein had already noticed something strange about black holes 2 years earlier. Bekenstein was a graduate student at Princeton when he realized black holes carried entropy. Entropy measures the number of microscopic arrangements consistent with the macroscopic state. A hot gas has high entropy because many molecular arrangements produce the same temperature. Bekenstein noticed that the area of a black hole horizon behaved exactly like thermodynamic entropy. When two black holes merged, the total horizon area always increased. Entropy never decreased. This mirrored the second law of thermodynamics with a precision too exact for coincidence. His advisor John Wheeler was skeptical. Hawking was initially dismissive of the connection. Hawking's 1974 calculation vindicated Bekenstein completely and deepened the mystery further. The entropy of a black hole is proportional to its horizon area, measured in Planck units. 1 Planck length is 10 to the power of -35 meters, the smallest meaningful scale. A stellar black hole horizon has an area of trillions of square Planck lengths of information. That surface area encodes the entropy of everything the black hole has ever swallowed. Here is where the holographic principle enters and makes the situation stranger still. The hole's three-dimensional interior contains less information than its two-dimensional surface. A volume of space is fully described by the information on its surrounding boundary surface. Gerard et Hooft and Leonard Susskind articulated this principle clearly in the early 1990s. Our entire observable universe might be the projection of information encoded on a distant boundary. The black hole information paradox sits at the intersection of holography and quantum mechanics. It refuses to be dissolved by either framework operating alone. Both are required simultaneously. In 1993, Don Page at the University of Alberta sharpened the contradiction considerably. Page calculated what the entropy of Hawking radiation must look like if information is preserved. Early in the evaporation, the entropy of emitted radiation should increase as the hole shrinks. At the halfway point of evaporation, now called the Page time, the entropy must turn around. This turnaround represents information beginning to leak out, encoded in quantum correlations. Hawking's original calculation produces entropy that increases monotonically until the very end. The Page curve and the Hawking curve are incompatible. One of them must be fundamentally wrong. Either information escapes, which means Hawking missed something in his original calculation, or information is genuinely destroyed, which means quantum mechanics has a fundamental flaw. Both options require rewriting physics at a deep level, which is why no resolution came quickly. The problem became more acute in 2012, when 4 physicists published a paper that worsened it. Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully, known together as AMPS, showed that preserving information creates a problem for the infalling observer as well. Their argument rested on 3 principles that each seemed separately unassailable on their own. First principle: information escapes the black hole in Hawking radiation, as unitarity demands. Second principle: nothing dramatic happens at the event horizon to a freely infalling observer. Third principle: the early and late Hawking radiation are not maximally entangled with each other. All 3 principles cannot simultaneously hold. At least one must fail, and the choice matters. If the second principle fails, then space-time is not smooth and empty at the event horizon. Instead of passing through an unremarkable boundary, an infalling observer hits extreme energy. AMPS called this a firewall, a surface of enormous temperature sitting at the event horizon. Any astronaut falling into the black hole would be incinerated before ever crossing the threshold. General relativity, which predicts smooth passage through the horizon, would be directly violated. The firewall seemed absurd. It also seemed logically necessary. Neither conclusion made it go away. The gravitational wave era has added a new observational dimension to the theoretical story. On September 14, 2015, the LIGO detectors in Louisiana and Washington heard space-time itself ripple. 2 black holes, each roughly 30 solar masses, had merged 1.3 billion light-years away. The signal lasted a fraction of a second and matched general relativity's prediction exactly. Binary black hole mergers have since been detected dozens of times by LIGO and Virgo combined. Each merger increases total horizon area of the resulting hole, confirming Bekenstein's area law. In 2021, a paper by Maximiliano Isi and colleagues claimed to test the area theorem directly. They analyzed gravitational wave data from the first detected merger event, GW150914. Before and after measurements confirmed the final hole's area exceeded the sum of the original 2. The area theorem held at the level of statistical confidence the data allowed. This was the first direct observational test of a theorem linking relativity and thermodynamics. Area increase is consistent with information loss and with preservation, the test distinguished. It confirmed that black holes obey the thermodynamic rules that make the paradox physically. You cannot have an information paradox if black holes have no thermodynamics. LIGO confirmed the thermodynamics. The information paradox stood exactly where it always had stood. The firewall debate drew a response from Joseph Polchinski himself in subsequent papers. Polchinski acknowledged the problem, but remained convinced the firewall was physically real. His view was that unitarity is sacrosanct. If the horizon must burn to preserve it, so be it. Others held the equivalence principle equally sacred. Smooth horizon passage must survive. No consensus emerged. The firewall debate became a decade-long program without a settled resolution. What AMPS accomplished was forcing the community to examine Hawking radiation's entanglement. Every subsequent approach, islands, ER equals EPR, fuzzballs, had to address the AMPS argument. The firewall was never proven to exist. It was never proven to be absent. It remains a conditional. If unitarity holds and the horizon is smooth, then something must give. Juan Maldacena at Princeton's Institute for Advanced Study had built a framework relevant here. In 1997, he published the ADS/CFT correspondence, one of the most cited papers in physics. ADS stands for anti-de Sitter space, a negatively curved spacetime with a specific geometry. CFT stands for conformal field theory, a quantum theory defined on the boundary of that space. Maldacena showed that gravity in the ADS interior is exactly equivalent to the CFT on its boundary. Two completely different descriptions of different seeming physics turn out to be identical. The same physical reality is described twice, once with gravity and once entirely without it. This duality became the most powerful tool for attacking the information paradox in the 1990s. In the CFT description, everything obeys quantum mechanics, and unitarity holds automatically. Information cannot be destroyed in the CFT, which means it cannot be destroyed in the bulk either. The paradox has a resolution. The question shifts from whether information survives to exactly how. The problem is that the duality tells you the answer without explaining the mechanism in the bulk. The holographic principle itself emerged from an attempt to make sense of black hole thermodynamics. Susskind had been troubled for years by what Hawking's 1974 calculation implied about information. He and 't Hooft independently concluded that three-dimensional physics encodes on a two-dimensional. Everything inside a volume encodes on its boundary, like a hologram projecting three dimensions. Susskind's 1995 book, The Cosmic Landscape, brought this idea to a wider audience for the first time. The principle implied a sharp limit. No region holds more information than its surrounding boundary. This bound, the Bekenstein bound, limits the information density of any physical system. A black hole saturates the bound exactly. Its entropy equals its area in Planck units. Nothing else in physics saturates the Bekenstein bound as tightly as a black hole does. This is not coincidence, but deep constraint. Black holes are maximum entropy objects by definition. Any theory that tries to store more information inside a black hole than its area allows will fail. The holographic principle constrains all of physics, not only black holes in particular. Samir Mathur at Ohio State University approached the problem from a different direction entirely. Through a series of papers in the 2000s, Mathur developed what he called the fuzzball proposal. His central claim was radical. Black holes have no classical interior in the relativistic sense. String theory replaces point particles with one-dimensional vibrating strings at the Planck scale. When enough strings collapse under gravity, they do not form a singularity with an empty interior. They form a fuzzball, a quantum string configuration whose surface encodes all the infalling data. The event horizon of a fuzzball is not a mathematical line, but a physical surface of quantum string. Information absorbed into a fuzzball is re-emitted in the pattern of string vibrations over time. The radiation is not purely thermal. It carries information encoded in the vibrational structure. Fuzzballs look identical to classical black holes from the outside at currently observable scales. No existing telescope can distinguish a fuzzball from a traditional general relativistic black hole. Mather built explicit fuzzball geometries for certain supersymmetric black holes in 5 dimensions. Those solutions were rigorous, but geometrically remote from real 4-dimensional astrophysical. Bridging from a toy fuzzball to a real astrophysical black hole remained difficult without a clear. Meanwhile, observations were catching up to theory in ways the paradox could not afford to ignore. On April 10, 2019, the Event Horizon Telescope released an image that changed public understanding. The target was the supermassive black hole in M87's core, 55 million light-years from Earth. The image showed a bright, asymmetric ring of glowing plasma surrounding a dark, circular shadow. The shadow's size matched general relativity's prediction within all observational uncertainties. 6 radio observatories spread across different continents had combined their signals coherently. The technique, very long baseline interferometry, gave the array an aperture the size of Earth. 2 years later, on May 12, 2022, the collaboration released an image of a second black hole, Sagittarius A star, the 4 million solar mass object at the center of the Milky Way galaxy. Located 26,000 light-years from Earth, it sits at the gravitational center of the Milky Way. Stellar orbits around the galactic center. Tracked for decades by Andrea Ghez at UCLA, had traced impossibly tight orbits around an invisible mass too compact for anything but a black. Reinhard Genzel in Germany independently led an effort that reached the same inescapable conclusion. The Nobel Prize in Physics 2020 went to Ghez, Genzel, and Roger Penrose for this collective work. Both images confirmed general relativity's predictions for the geometry and scale of event horizons. No firewall appeared, and a Planck-scale firewall would be invisible to any instrument in existence. The observations confirmed that black holes exist and behave as general relativity predicts they. The paradox, however, lives at the quantum scale, where no image and no telescope can yet reach. The theoretical pressure peaked in 2019 when Ahmed Almheri and Jeff Pennington published papers. Both independently reached the same structure, now called the island formula for black hole. Consider the Hawking radiation streaming away from an evaporating black hole over its full lifetime. The radiation carries quantum correlations between particles emitted at widely separated times. Early and late radiation are entangled in ways that classical thermodynamics cannot account for. When you compute the entropy of the radiation, something unexpected must be included in the sum. Deep inside the evaporating hole exist quantum island regions entangled with the exterior radiation. These islands cannot communicate classically with the outside. No signal escapes the horizon, but they contribute to entropy through a quantum gravitational mechanism without classical analog. When island contributions are included, the entropy of the radiation follows exactly the Page curve. It rises early in evaporation, peaks at the Page time, and decreases as expected from unitarity. The paradox appears resolved in principle. Information escapes encoded in long-range quantum. The mechanism involves quantum extremal surfaces, which generalize the Bekenstein entropy formula. Entropy is not simply the horizon area divided by 4 in the full quantum gravitational theory. It equals the area of the extremal surface that minimizes a generalized entropy functional. Early in evaporation, the minimizing surface lies outside the hole, and entropy follows Hawking. At the Page time, a new surface deep inside the hole, the island boundary, becomes the minimum. The transition is automatic, determined by the mathematics, and produces the Page curve exactly. Almhiri, Pennington, and collaborators developed this framework extensively through 2019 and 2020. Many physicists called it the most significant progress on the information paradox in decades. Netta Engelhardt at MIT, who had developed the quantum extremal surface formalism with Aaron Wall, recognized in the Island papers the application of the technical tools she and Wall had built. Daniel Harlow at MIT added a connection to quantum error correction that clarified the picture. He showed that the CFT naturally encodes black hole interior data like an error-correcting code. The black hole interior is the encoded message. The Hawking radiation is the redundant encoding. Recovery of the message, getting the information back, is possible even after partial data loss. The Island formula had a peculiar implication that Almhiri and others noted with some care. It suggested that the black hole interior was encoded redundantly in the exterior Hawking radiation. An observer collecting all Hawking radiation could, in principle, reconstruct the entire black hole. An infalling observer crossing the horizon would have direct access to that exact same interior. This apparent duplication of information, existing simultaneously inside and outside the hole, was precisely the double counting that had pushed Susskind and Hooft toward holography before. Susskind named this black hole complementarity. The information appears in a different place for. No single observer sees the same information twice. Quantum mechanics is never violated locally. The information resides in radiation for the outside observer and in the interior for the infalling. Both cannot compare notes. The geometry itself prevents them from meeting and exchanging data. Black hole complementarity provided a way to accept dual encoding without logical contradiction. But it required abandoning the idea of an absolute, observer-independent description of reality. What exists depends on who is asking and from which side of the horizon they are asking from. This ontological shift was philosophically uncomfortable, but seemed to be what the physics required. But the Island formula came with caveats serious enough to prevent any celebration of resolution. The derivation relied on the replica trick, a technique borrowed from statistical mechanics. The replica trick computes entropy by analytically continuing a discrete counting parameter. It works reliably in known systems, but its validity in quantum gravity has not been established. The derivation also relied on Euclidean path integrals that sum over geometries in imaginary time. Those path integrals include contributions from configurations called replica wormholes. Replica wormholes connect different copies of the geometry in ways without obvious physical meaning. Whether they represent real processes or saddle point artifacts of the calculation remains. Douglas Stanford at Stanford has explored the physical meaning of replica wormholes carefully. The Jackie Wu Teitelbaum model, a two-dimensional gravity theory, serves as a controlled test case. In that toy setting, the Island formula can be derived more rigorously and explored in more detail. Two-dimensional gravity may omit features essential to four-dimensional black holes in our universe. This gap between toy model and physical reality runs through the entire field like a fault line. All exact calculations are done in simplified settings, where the mathematics becomes tractable. Real black holes form from collapsing stars, live in four dimensions, and inhabit an expanding. None of the exact calculations apply to that physical setting. It may be mathematically. The firewall problem from 2012 was not simply dissolved by the Island formula's arrival. Juan Maldacena and Lenny Susskind proposed in 2013 a connection between entanglement and wormholes. Their proposal was condensed into a single equation-like statement: ER equals EPR. ER stands for Einstein-Rosen bridge, the technical term for a wormhole connecting two regions. EPR stands for Einstein-Podolsky-Rosen, the 1935 paper that introduced entanglement to physics. If every entangled pair of particles is connected by a microscopic wormhole, the firewall reframes. An infalling observer is not hitting a wall. they are passing through a wormhole to the exterior. The entanglement between the black hole interior and Hawking radiation becomes geometric connection. This picture has aesthetic appeal and mathematical support at the qualitative level. It does not yet constitute a complete theory, and its precise content remains actively debated. Patrick Hayden at Stanford, working with John Preskill in 2007, had established an important result. After the page time, information thrown into a black hole comes back out in a nearly immediate. A quantum computer with access to all pre-page time radiation could, in principle, recover the data. The computation is exponentially hard in practice. No actual computer could perform it. This, the Hayden-Preskill problem, became the benchmark against which all later proposals are. Any complete resolution of the paradox must explain how that decoding is possible in principle. Hawking returned to the problem near the end of his life with Malcolm Perry and Andrew Strominger. In 2016, they proposed that black holes carry soft hair, massless quantum excitations at the point. Soft particles are real photons or gravitons with energy approaching zero in a precise mathematical. They accumulate without energy cost and might encode information as it crosses the event horizon. Soft hair attracted genuine interest, alongside skepticism about its total information storing. Hawking died in March 2018, leaving the paradox that bore his name still fundamentally unresolved. His 1974 paper created the crisis. His final papers gestured at solutions he never lived to. The community he had built kept working, carrying his questions into decades he never lived to see. Alexei Kitaev had been developing a different angle on the problem in his work on quantum chaos. In 2015, he showed that the Sachdev-Ye-Kitaev model was dual to a simple two-dimensional gravity. The SYK model is a system of randomly interacting quantum particles with unusually rapid scrambling. Scrambling measures how quickly a system spreads information across all its available degrees of. Black holes are the fastest scramblers in nature. They saturate the theoretical chaos bound. Hayden and Preskill had anticipated this result, and the SYK gravity duality confirmed it precisely. The connection between quantum chaos, scrambling, and black hole physics opened new theoretical. Fast scrambling describes information spreading, not recovery. The two are fundamentally different. By 2024, the island formula had become the dominant framework in information paradox research. Tom Faulkner at Illinois and others continued scrutinizing the formula's mathematical foundations. The replica wormhole terms producing the island result assume a specific gravitational path. In quantum gravity, summing over all geometries in a path integral is not a mathematically defined. The island formula works formally, but lacks the rigorous mathematical foundation physicists expect. This is not unprecedented. Formal results in physics often precede rigorous proofs by many years. But the information paradox has a history of proposals that seemed to work until they didn't. Hawking's original calculation appeared entirely correct until its implications became unacceptable. AMPS appeared logically airtight until researchers found potential loopholes in each assumption. Appropriate skepticism about clean answers is therefore standard practice in this specific field. The deepest problem Hawking himself identified cuts below the technical details of any proposal. The information paradox exposes a gap in the foundations of physics, not just in black hole physics. Quantum mechanics describes the evolution of states in a fixed background space-time arena. The background might be flat, curved, or anti-de Sitter, but it is always a fixed external given. When that background becomes dynamical, when space-time itself fluctuates quantum mechanically, the standard framework of quantum mechanics does not know how to proceed in a principled way. The wave function of the universe is not defined within current mathematical physics. Black hole evaporation involves dynamical space-time. The horizon forms and then disappears. Any genuine resolution of the paradox requires understanding quantum mechanics in that regime. or it requires modifying general relativity at the quantum level in ways nobody has yet written. Or, most likely, it requires a new theory that contains both frameworks as limiting approximations. This new theory is called quantum gravity, and it does not exist in complete form anywhere today. String theory is the most developed approach and has produced fuzzballs, holography, and ADS/CFT. Loop quantum gravity quantizes spacetime geometry directly without invoking extra dimensions. Asymptotic safety, causal dynamical triangulations, and other programs have their serious advocates. None has produced a prediction testable with current or near-future experimental technology. The information paradox sits inside this theoretical void, unresolvable without the missing theory. What distinguishes the paradox from other open problems in fundamental physics is its accessibility. You can explain it to a physics undergraduate in 30 minutes using concepts they already have. Quantum mechanics preserves information. General relativity erases it inside black holes. Both cannot simultaneously be correct about the same physical situation. One of them must bend. That clarity has made it a benchmark. Any candidate theory of quantum gravity must address it. A theory resolving the paradox passes a necessary test for correctly describing physical reality. A theory that cannot resolve it has failed at the first serious checkpoint and needs modification. In 2023, a team from Caltech, MIT, and Harvard ran an experiment on a quantum processor. They simulated a quantum teleportation through a wormhole using the SYK model as their system. The experiment demonstrated the theoretical prediction of the SYK gravity correspondence cleanly. It did not create a real wormhole or test quantum gravity in any direct physical sense, but it demonstrated that the theoretical frameworks connecting gravity and quantum mechanics had. As quantum hardware improves, simulations of quantum gravitational effects will grow more precise. Patrick Hayden has been asking what experimental signatures the island picture actually predicts. If information escapes through the island mechanism, Hawking radiation is not perfectly thermal. It carries quantum correlations that distinguish it from a perfectly thermal, idealized distribution. For stellar black holes, these corrections are too tiny for any imaginable instrument to measure. For microscopic black holes, if they exist, corrections might fall within some theoretical reach. The Large Hadron Collider found no evidence of microscopic black holes in its operating runs. The extra dimensions that would allow their production appear excluded at currently probed energies. The Planck energy scale sits 16 orders of magnitude beyond what the LHC can probe. Experimental resolution will not come in the near future and may not arrive in any of our lifetimes. Resolution, if it arrives, will come through insight. Someone finally seeing the structure. Physics has examples of problems that seemed intractable for generations before suddenly yielding. The ultraviolet catastrophe resisted explanation until Planck introduced quantized energy in 1900. Chemical bonding was mysterious until quantum mechanics provided the right framework in the 1920s. Maxwell unified electricity and magnetism by realizing that changing electric fields produce. Each breakthrough required accepting something that seemed unnecessary before its clarifying moment. The paradox may require accepting that space-time is not a truly fundamental feature of the physical. Space and time might emerge from something more primitive, just as temperature emerges from atomic. In that case, the question of where information goes inside a black hole may be ill-posed. The question is meaningful in the space-time description, but dissolves in the underlying theory. This is what ADS/CFT suggests, though it says it without fully spelling out the mechanism. The boundary CFT contains no gravity and preserves information trivially through quantum mechanics. The bulk gravitational theory must also preserve information since the two complete descriptions. Translating that boundary preservation into a bulk mechanism is precisely what the island formula, and the island formula waits for deeper mathematical justification that nobody has yet provided. The SYK model had another contribution to make beyond the scrambling bound result. Kitaev's 2015 talks showed that SYK was solvable in a specific large N limit using replica methods, the same replica methods that appear in the derivation of the island formula for black hole entropy. This was not coincidence. Both calculations probed identical underlying physics from different. The SYK model has no spatial dimensions, no geometry, and no notion of a black hole horizon. Its thermodynamics, scrambling properties, and entanglement structure closely mirror A. Studying SYK is studying black hole physics without the complication of actual spacetime. SYK became a laboratory where ideas about information could be tested before applying them to real world. Several groups used the SYK model to probe questions about the page curve and information recovery. The results have been consistent with the island picture. Unitarity holds, information escapes. But they have not clarified the physical mechanism, only confirmed the mathematical consistency. The SYK model proves information survives without explaining how it crosses the horizon. Erik Verlinde at Amsterdam has long argued that gravity is emergent rather than fundamental physics. His entropic gravity program derives Newton's gravitational law from thermodynamic principles. If gravity emerges from entropy, the Bekenstein-Hawking area law is no longer a coincidence at all. It becomes the foundational equation from which gravity follows, and the whole paradox reframes. Verlinde's entropic gravity program attracted serious engagement and serious technical objections. It remains a research direction with unresolved issues that its author openly acknowledges. Mark van Ramsdonk at the University of British Columbia contributed a crucial piece of the picture. In 2010, Van Ramsdonk showed what happens when you reduce entanglement between boundary regions. The space-time in the bulk breaks apart into disconnected pieces as entanglement approaches zero. Restoring entanglement reconnects the space-time. Geometry is literally woven from quantum. This result, combined with the ER equals EPR conjecture, points toward a unified picture. Spacetime is a fabric of entanglement. Geometry is the macroscopic shape of quantum correlations. Black holes are where the entanglement structure becomes extreme and starts to dissolve. Information falling into a black hole alters the entanglement structure of the horizon measurably. That altered entanglement propagates outward through Hawking radiation over the full evaporation. The page curve follows from entanglement structure. The island formula quantifies the relationship. This picture is coherent and internally consistent. It also lacks precise mathematical formulation. Tensor networks capture qualitative features of holography without serving as exact quantitative. Translating the entanglement as spacetime intuition into testable predictions remains ongoing work. By 2025, the theoretical picture had changed considerably from where it stood when AMPS first. The island formula showed the page curve can be reproduced within frameworks physicists already. ER equals EPR gave a qualitative picture in which entanglement and geometry form a single, unified. Tensor networks gave researchers explicit constructions to probe the entanglement geometry link. But the bulk physical mechanism by which information escapes the black hole remains essentially. Replica wormholes do the mathematical work in the derivation, but their physical meaning remains. Whether they represent real spacetime configurations or formal artifacts remains an active area. Shinseiryu and Tadashi Takayanagi published in 2006 a precise formula relating entropy to geometry. The RT formula states that boundary entanglement entropy equals the area of a minimal surface in. This created a precise and calculable bridge between quantum information theory and classical. Faulkner, Lukovich, and Maldacena extended the RT formula in 2013 to incorporate one loop. Extended the RT formula to include quantum corrections from fields propagating in the bulk. Amhiri, Engelhardt, Harlow, and Horowitz used this extension directly in the island papers. Each step built on the last in the way that characterizes a research program gaining coherence. The Planck scale physics, where quantum gravity actually operates, remained entirely beyond. The question Hawking opened in 1974 remains unanswered at its deepest level as of 2025. Not because the field has failed. The progress since 1974 has been genuinely remarkable. ADS/CFT alone transformed theoretical physics in ways extending far beyond the paradox itself. But genuine resolution requires understanding quantum mechanics and gravity at the Planck scale. That regime is beyond experiment, and the theoretical language for it does not yet fully exist. The window Hawking's calculation opened onto quantum gravity is still the clearest view we have. Everything beyond that window, the interior, the singularity, the final moments of evaporation, lies in territory where current theory can gesture but cannot yet calculate with confidence. The information paradox is not a failure of physics. It is physics reaching the edge of its day. Every generation inherits the tools of the previous and uses them to push closer to the boundary. Each push reveals previously invisible structure, and each new structure generates the next set of. The paradox generated holography. Holography generated ADS/CFT. ADS/CFT produced the island formula. The island formula generated questions about replica wormholes and the nature of space-time itself. That chain of questions leads somewhere real, even if the destination is not visible from here. John Wheeler, who supervised Bekenstein and who coined the phrase "black holes have no hair," also said that every good question carries within it the seed of its own answer. The condition is that the question must be asked with sufficient precision to reveal that seed. The question of what happens to information in a black hole grows more precise with every decade. The answer is not yet visible, but the question is sharper than it has ever been in 50 years. Somewhere in mathematics not yet written, the information paradox has a resolution waiting to be. Whether that resolution resembles the island formula or something entirely different remains fully. What is not open is that finding it will require understanding quantum gravity at its foundations. When that understanding arrives, it will reshape cosmology, the nature of time, and the origin of. There is a broader context for the information paradox that physics rarely makes explicit. The paradox exists because two extraordinarily successful theories stand in direct contradiction. Quantum mechanics has passed every experimental test conducted since 1925 without a single failure. General relativity has passed every test since 1916, including some of the most precise in all of. Both theories are correct in their domains. Both theories cannot both be correct in the same domain. Black holes are the only natural environment where both domains overlap powerfully at the same. On Earth, quantum gravity effects are suppressed by a factor of roughly 10 raised to the power of. The Planck mass, the scale at which quantum gravity becomes important, is about 22 micrograms. Detecting it in a lab would mean measuring gravity from a 22 microgram object held in superposition. The singularity at the center is where both theories simultaneously reach their breakdown point. The Hawking radiation at the horizon is where their conflict becomes visible to outside observers. The information paradox is not just a puzzle about black holes. It is a diagnostic for all of. It tells us exactly where and how our two best theories of nature are incompatible with each other. Resolving it would not just explain what happens inside a black hole. It would explain much more. It would provide the missing link between quantum mechanics and general relativity. It would be the discovery that defines the physics of the 21st century. The problem Hawking encountered while calculating quantum fields near a curved horizon in 1974 is not a technical puzzle about the fate of matter. It is a question about the structure of reality. That is why 50 years of the sharpest theoretical minds have not yet resolved it completely, and why the next 50 years of fundamental physics will be shaped, in part, by whether they do. Thank you for staying with us until the very end of this journey through deep time. If this exploration moved you, subscribe and stay for the next ancient chapter. Your curiosity is what keeps these lost worlds alive.